going on, everybody? It's Mr. Gustin. I'm in the physics conference room. Today we're dealing with combo circuits. I've got a combo circuit on the board behind me. I've got a data table. The challenge here, the task here, the question I'm asking is for us to figure out the voltage, the resistance, and the current at each of the resistors, and then obviously at the total or the equivalent resistance as well. Okay, that's the goal. We've got to figure this all out. Now, this would be super easy. We've gone over series circuits. We've gone over parallel circuits. Let's go ahead and look at this circuit. If I look at this circuit, I see that there is a battery, a 9-volt battery. It sends some current up and through. These two resistors are in series, which is nice. These two resistors are in series, which is nice. But like this set of resistors and this set of resistors are in parallel. And so that's weird. Like it's neither a series circuit nor a parallel circuit. It's both all at once. So I'm going to have to rely on some junction rule stuff, some loop rule stuff, and some of my tricks of series versus parallel circuits. So we're working those things together, okay? Here's the plan. Let's start by analyzing this. I've got my total voltage. I don't know what my total current is, and I don't know what my total resistance is. I will say this, though, that I know since these are parallel circuits, that there's a loop here and a loop here, I know that this branch gets 9 volts, and that this branch gets 9 volts. I know that because it's a loop back to the battery. That's the loop rule. But I don't know how much current is through this branch, so I can't necessarily figure out how much voltage each of these gets. So what we're going to do is we're going to figure this out. But it would be much easier if I just smash these together. If I just go ahead and smash these two resistors together over here. Let's treat this as if it is one single 50 ohm resistor. And let's treat this over here as if it's one single 150 ohm resistor. When I do this, I can actually figure out the current moving through that branch because now I have an overall resistance. I haven't filled anything in my table yet, but now I know that at this junction, some current is going to go this way and some will go this way. And I know that with 9 volts here and a total of 50 ohms resistance, I can figure out what the current through this branch is. So let's go ahead and do that. To figure out current through this branch over here, let's go ahead and take 9 volts, which is total voltage. That's equal to the 50 ohms resistance times the current in, let's call it the 1-2 branch. When I do this, my current 9 over 50, what do I end up getting? 9, 50. I end up with, what is it? 0.18 amps through this branch. Now, when I think about this, these are in series. Because they're in series, they receive the same current through both. I can now fill in at resistor 1 and 2. They both get 0.18 amps of current. 0.18 amps of current. I can do the exact same process for a very similar branch. And it's got more resistance in this branch, but it's the same process. Come over here. They get 9 volts because it's a loop back to the battery. I got 150 ohms over here. I would expect a lot less current to go through here, but 9 over 150 is 0. This would be the current at 3.4. The current at 3.4, this is 1.2, is equal to, I think it was 0.06 amps. That's a lot less current because there's a lot more resistance. 0.06 amps, 0.06 amps. Now, if I look at this, I remember my loop rule. My junction rule. Current in equals current out. This is my out current. This is my in current. So whatever current enters this point and splits must be rejoined and make its way back to the battery. So let's look. What's the current in this branch? 0.18. What's the current in this branch? It's 0.06. The total of those two, 0.18, 0.16, ends up being 0.24 amps. That's the current that flows through this wire and this wire that eventually splits at those two junctions. Now, from this point on, I've got current resistance at every resistor. I've got a voltage and a current here. I can fill the rest of this in, so let's go ahead and do it. I'm just going to fill this guy in here. I'll use Ohm's law. I've got voltage divided by current to find overall resistance. 9 divided by 0.24 is 37.5. That's my overall resistance there. Let's stop and think for a second. Does that make sense? Does it make sense that the overall resistance is 37.5? What I know about parallel circuits is that adding branches in parallel decreases the overall resistance. So the resistance in this branch is 50. The resistance in this branch is 150. My total resistance should always be, in a parallel circuit, less than either of the parallel branches. And it absolutely is. That's the principle behind parallel circuits, is that adding resistors in parallel decreases the overall resistance. Remember our straw demonstration, okay? So I got that down. Let's go ahead and just knock the rest of these out. I got 10 times, I can just do that in my head, 1.8 volts here. This guy right here should be the difference between 1.8 and 9, because again, that's my loop rule, so it should be 7.2 volts. Let's check it using Ohm's law. 40 times 0.18, yep, it is. Boom, 7.2, perfect. Over here, 100, 1, 2. This should be 6 volts over here. And again, this is a loop, so this should be the remaining voltage in that loop. 6 and 9, this should be 3 volts. And if I take 0.06 and multiply by 5, I end up with 3 volts. This is exactly how we would attack a combo circuit. Now, every combo circuit is different, so you can't follow a certain set of rules. Just understand we are relying consistently on loop rule and junction rule, and then our series and parallel circuit equations to figure this out, okay? We've done one in class, done one here. If you got any questions, email, drop in the comments, ask me in class, whatever you need. Until next time, see ya.